All right, welcome back to electron configuration. So what we're looking for here is how do we form, or how do we recognize the ticket to the stadium, the ticket to the periodic table? Well, again, our interest is hydrogen. So we're going to have to start at hydrogen and then move our way forward. So we're going to use large numbers for the rows. We're going to use letters like S, P, D, and F for the sections. And then we have superscripts for the seat numbers. So notice in this situation here, what we're going to show you is that this is really just the row. That's the period. The letter is just the section or the subshell. And then the superscript is like the box, like the seat. And then as you go and fill your stadium, you just keep going until you land at your location. And that typically tells you your valence electrons. Your valence electrons are always your highest S and P electrons. So if they're your highest S and P electrons, they're always going to be in this highest most level, which in this case is a 4. S and P, there is no P here, it's just a 1. So this would be in Roman numeral 1 as a family. And that's where potassium sits, just like lithium and sodium that we saw earlier. So the only way to get good at electron configuration is to practice it. And in reality, it's a huge chunk of your homework. It's a huge chunk of the exam for this chapter because it's the underlying feature of the last several videos. This is just building up to it. So what is the electron configuration for silicon? So let's jump screens. And we can use our periodic table from class. And let's use black because it's going to show a little bit better. So again, here's our entrance. So here's our door to the stadium. So you have to enter here. As we enter here, we're going to write 1 because it's in period 1. So we would say 1. In the periodic table, we have 4 sections. We have this section here that's tall and skinny. This is called the S section. What comes next is the section over here on the right. This is what we call the P section. For very few examples in Introchem, you might use this section, which is called the D. And then underneath is the section that is least used in Introchem, but it is part of this concept, and that's the F. So as we make our way to silicon, which is over here, we need to count boxes till we get there. So this would be 1s1. This would be 1s2, so we write 1s2. Because notice there is no more elements in this periodic table, because again, helium belongs over there by 1s2 in this model. The only reason they throw helium over here is because it's a noble gas. It's full, so they put it with the rest of the elements that are full. But notice that was number 2, so in order to restart, there's no more elements over here, so we have to restart in row 2. So that's why I write number 2. This is still the S section, so this is really just 2s1 and 2s2, so we write 2s2 because it's full. We continue across the periodic table, and after element 4 is element number 5, notice we're in a new section. We're still in the second row, so we still use the number 2, but now we're in a new section. This is called the P section. And then we count boxes across. This would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, so we write 2p6. Again, all of these are P, all of these are in the second row, second period, the second energy level from the nucleus. No more elements, so we have to restart again. So then we get to 3. And notice this is just a continuation vertically. This is now 3s1 and 3s2, so we write 3s2. We continue across to aluminum, which is still in the third period. Right, the third period still continues across. This would be a 3p1. This would be a 3p2. So we're going to write 3p2 as an answer. So you can see that really it's these last sections that kind of tell us where we're at. 3p2 is going to tell us our location. But everything else is just a filling of the seats of our stadium until we get there. And that's what we want. So notice we have the 3s2, 3p2. When it comes to valence electrons, what we're after in that situation is to remember valence electrons are on the outside. So if valence electrons are on the outside, find your highest energy level, which is a 3. Find your s and p electrons, which we have some of both. And then count the superscripts. 2 plus 2 equals 4 valence electrons. So we'd expect to see this in family 4, which is IV. And that reminds us of Roman numerals being very important, telling us the valence electrons because they're always at the end of electron configurations. What we'll notice here, this is just a noble gas. We would call this a neon. It's the 10th element on the periodic table. It represents the first 10 boxes of the periodic table. And then if we were to write 3s2, 3p2, that would just be a shorthand version that we'll see a little bit later called noble gas configuration. And here it's a whole lot easier to see the 4 that actually matter for at least the smaller elements. That's true. So we did a simple example. It may not all seem simple because, it's new and everything new is scary. But what we didn't do is an example that shows you a little bit deeper into the periodic table, and that's when we get into the d electrons and the f electrons. Again, f we won't probably see too much in chemistry class just because it's a little too deep into the periodic table for introductory purposes of chemistry classes, but the d section we will see a little bit, and we have to be mindful that because of that balcony we saw in the previous video where the 4 gets a little too low, the 3 gets a little too high, you have to remember that in the D, you have to subtract 1. Just like if you're in Gen Chem, the F, you'd have to subtract 2 of our periods. So even though this is 4s1 and 4s2, this is really 3d1 all the way to 3d10. So it's always 1 electron behind because this is what happens when that 4th energy level splits 4 ways. The 3rd energy level splits 3 ways. That overlap, that balcony, forced us to switch our levels, so to speak. So be mindful of that. That's the only discrepancy that we have to worry about in the periodic table. So notice as we go to bromine. So let's jump screens and show you what bromine looks like and show you how it kind of jumps past that balcony feature of the periodic table. So in this situation, we have to, again, start with hydrogen. So starting with hydrogen, we would write, we'd finish this box and this box. So we would just write 1s2. No more elements because we already used this one. So again, don't worry about this one. It belongs over here with respect to this concept. After 2 comes 3. In the periodic table. So we restart. As we move across these, we would say 2s2. Much like before, we would skip across, and then we go through this section, and that would be 2p6. That's the neon configuration. After 10 comes 11, so we continue again through the next 2. That would be 3s2. Continue through the next section here. Notice it's going to be very similar as this one. It's just going to be 3p6 instead because it's in the next row away from the nucleus. We continue again with a 4s2. But now be careful. This is the D section. This is 3d1. So as we go across, that's going to be 3d10. And then as we go to bromine, we go a little bit further. Notice we only go 1, 2, 3, 4, 5 boxes further. So that would be a 4p5. When it comes to valence electrons, which is what they were indicating on the previous set of notes, look for your highest energy level, which is a 4. 3D is in a lower energy level, so we ignore it. We look at the 2, we look at the 5. Together that's 7 electrons in the valence electron concept, and that would be Roman numeral VII, or a halogen. That's exactly what we see here. So because of that balcony overlap, we see that indicated from the picture over here. So notice that 4s, 3d kind of superimpose each other, so just be aware of that. That shows up here. Watch out for those to be switched in the homework, because if they're switched, they're wrong. In the periodic table, we proceed between these two elements before we ever get to these 10 elements. So go in perfect order. You should move 2 boxes in the first period, then 2, then 6, then 2, then 6, then 2, then 10, then 5. All of those equal bromine. So be careful. You can add those numbers together even. 2 plus 2 is 4, plus 6 is 10, 12, 18, 20, 30, 35. That's 35 electrons. That's the atomic number of bromine. And that would be true for elemental bromine, that it has 35 electrons. So what about for iron? How many valence electrons in it? So let's take some practice. So again, let's jump back to our periodic table and then practice it. So again, you have to start and enter the stadium at hydrogen. Helium, again, belongs right here. So this is 1s2. Then there's no elements left. So we restart on the left and we say 2s2. We go through the entire next section, that's 2p6. Through the next section we go 3s2. And then 3p6 for this section. Again, that's representing that entire distance. We're now in period 4, so that's 4s2. It's S section. It's 2 boxes wide, so that's a superscript of 2. Then we count over to iron. That's 1, 2, 3, 4, 5, 6. So be careful. This is 3d6. So 3d6 is because we went 6 into the d section, but because of the balcony, this is actually the 3rd energy level. That's the part of the 18, the 2n squared idea from the other video, that gives us the 18 electrons from the 3rd orbit that we would expect to see. So look for a 4s2 3d6. And that's what we see here. So when it comes to valence electrons, what do we see now? Well, something unique happens with the transition metals, and that's that they all have 4s2, or a 5s2, or a 6s2, or a 7s2 that precede them. And because this is a highest energy level, because this is an S, these have 2 valence electrons. And if it has 2 valence electrons, that means that they can lose those electrons, and a lot of transition metals end up being a +2 charge. Not all of them, but most. And this is why. They can lose these electrons here and still be full, at least relatively speaking. They're going to still have some leftovers. And that's what makes them transition between charges, and that's what we'd expect here. But as far as valence electrons go, Roman numerals aren't as helpful in this series because they can switch around a little bit, but for the most part, you can just look for their preceding s electrons and know that everybody in the d section has 2 valence electrons based on this theory. They're going to have 2 electrons, and they're going to feel like a +2 when there's other elements around like nonmetals to gain those electrons, as we'll see at the end of this video. Eventually we can get into the noble gas core configurations. Again, this is just using noble gases to shrink our electron configurations to make our ticket to the stadium not look so complicated. So if we look at this example here, we can see that here is helium. This would be 1s2 helium. If we go to the entire next section, which is 2p6, and chop it here, that would just be neon. If we go all the way to here and chop, that would be argon. And we can continue through krypton and eventually through xenon. So notice, with the exception of helium, it's always a P6 that is a noble gas, because they're always at the end of the P block of the periodic table, the P section of the periodic table. Notice we never really reached the next noble gas. So if we take our last noble gas, which is all of these, all the way to here, that's what xenon is. And then we take what's left over, which in this case is quite a bit, and then we put that afterwards. When it comes to recognizing valence electrons, we're still just looking for highest energy level. So if we want highest energy level here, let's find energy level 6, energy level 6. 5s are lower, 4s are lower. All that really matters is these 2 electrons and these 2 electrons. Those are 4 electrons total. Those would be in the valence. And the scale tells us that it's in Roman numeral IV, or 4, just like carbon. So even though lead is gigantic, on the outside it looks just like carbon with 4 electrons. So electron configuration is just a great way for us to theoretically show what's on the outside, what's underneath. What's underneath is called a core. So oftentimes that's a noble gas. And getting to that core of a noble gas is always the hope, the dream of a lot of elements. So their ability to lose and gain electrons is going to be very important, because they can show us how many electrons do we need to fill electron configuration to make a noble gas, or how many electrons do we need to take away. Or is the case with many of our transition metals, how many are going to be left over that we can dip into to get to other charges that they can transition to. So if we look at this configuration here, really what we're looking for to cheat in our homework in a lot of cases is look at the end, 4p3. So if we wanted to know that this was arsenic without going through a lot of work, we could use the element argon, go 2 boxes, go 10 boxes, go 3 boxes, or just use 4p3. Let's show you how that works. All right, so if we wanted to go to 4, P3, that was the end of our configuration, we would go 4, we would go P section, and once we get to the P section, we would go over 3, so 1, 2, 3, and bingo, there's arsenic. We could have also said go to argon, which is here, go to 4s1, 4s2, go to 3d1, 3d2, 3, 4, 5, 6, 7, 8, 9, and 10, and then go to 4p1, 2, and then 3. So either way, those are ways to think about how to get to those elements very quickly. Either look for 4p3, go to the 4th row, go to the p section, go to the 3rd box, or go from argon and then count boxes all along the way, and you get to the same location. And that should be the easiest way to tackle a lot of your homework very quickly. So in a separate video, we're going to show you, using electron configuration, how can we determine things like size or energy. And then a little bit later, we'll talk about how we can put these elements together to make ions, and then how ions can interact together to make compounds. And we'll see you then.